Now in this lecture we'll find out the area of the small circle. In the drawing we have a semicircle. This is a semicircle. Line segment AQ equals to 2 units in its length. Line segment TB equals to 8 units in its length. This is angle PQA. This is a right angle. This is angle STB. That is also a right angle. Inside this semicircle we have this small circle. And our mission is to find out the area of this small circle. So first of all, we will define the points that are relevant to this question. Define the points that are relevant to this question with letters. We will define the center of this big semicircle. This point is point H. We will define the center of this small circle. This point is point K. We will define the point of tendency of tangent AB with this small circle. This point is point M. We will define the point of tendency of tangent ST with this small circle. This point is point L. And finally, we define the point of tendency of tangent PQ with this small circle. This point is point G. AB is the diameter of this big semicircle. Therefore AB is the diameter. It is absolutely a straight line. Okay, repeat again. AB is the diameter of this semicircle, therefore it is a straight line. So if we focus on the upper side of the straight line AB, at point Q, here the sum of the angles in the upper side of AB at point Q must be equal to 180 degrees, according to rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? You have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we focus on the upper side of the straight line AB at point T. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll join points K and M together by a straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and ends at point M, that is the point on the small circle itself. So this is exactly the definition of a radius. Therefore, Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x, according to our definition. So here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and this is tangent AB that is tangent to this circle at this point, point M. And here the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius Km that equals to x. The radius Km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we join points K and G together by a straight line. KG is the radius of this small circle, is equals to x, according to our definition. Again, we have the radius Kg that is drawn to point G, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius GK. If PQ is perpendicular to GK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually, by doing this construction, we created a quadrilateral GKMQ. Inside quadrilateral GKMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral GKMQ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrilateral GKMQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle GKMQ, side GK must be equal to the opposite side QM. But GK equals to x, therefore QM must be also equal to x. Likewise, according to the same rule, in the same rectangle GKMQ, side KM must be equal to the opposite side GQ. But KM is x, therefore GQ must be also equal to x. So actually found out that quadrilateral JKMQ is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. So I write it down. This quadrilateral GKQM is a square. Likewise, we join points K and L together by a straight line. KL is the radius of this small circle. That's equal to x according to our definition. Again, we have the radius KL that is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LK. If ST is perpendicular to LK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral KL edge M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral KLTM, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So let this quadrilateral KLTM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the same rule, in the same rectangle KLTM, side KM must be equal to the opposite side TL. But KM is x, therefore TM must be also equal to x. Again, but we found out that quadrilateral KLTM is not a rectangle but a square, because of the fact that all of its sides are equal to each other. So I write it down. This quadrilateral KLMT is a square. So here we have this angle GKL. Angle GKL, this is angle GKL. This is equal to 90 degrees plus 90 degrees, it is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined, it is a straight line. So GKL is a straight line. If GKL is a straight line, it means that GL is also a straight line. So GL is a straight line, but GL is a straight line that touches the circle at 2 points, point G and point L. And therefore, GL is a chord, because any straight line that touches the circle at 2 points, it is defined as a chord. So GL is a chord, but GL is a chord that passes from point K, that is the center of this small circle, and we know that any chord that passes through the center of the circle, it is defined as the diameter of the circle. Therefore, GL is the diameter of the small circle. So I'll write it down. We actually found out that 97 GL is the diameter of this small circle. GL is the diameter of the small circle. In the next step, we'll focus on shape GLTM. In the next step, we'll focus on shape GLTQ. In this shape GLTQ, we have 1, 2, 3, 4 sides. Again, in shape GLTQ, we have 1, 2, 3, 4 sides. Side GL, it is absolutely a straight line because it is the diameter of the small circle. So in total, in shape GLTQ, we have 1, 2, 3, 4 sides. And therefore, shape GLTQ is a quadrilateral. So shape GLTQ is a quadrilateral that has 1, 2, 3, 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this shape GLTQ or we relate to quadrangle GLT cube. It's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle GLTQ, side GL must be equal to the opposite side TQ. But GL is the diameter of this small circle that equals to 2x. Therefore TQ must be also equal to 2x. So I write it down. TQ equals to 2x. What is the radius of the big semicircle? Actually, the radius of the big semicircle equals to the diameter of the big semicircle, that is AB over 2. So we will define the radius of the big semicircle as capital R, and capital R, that is the diameter of the semicircle according to our definition, equals to AB over 2. AB is the diameter over 2. What is the length of AB? The length of AB in total equals to 2 plus 8. 2 plus 8, that is 10 plus 2x. So AB in total equals to 10 plus 2x. So the diameter AB equals to 10 plus 2x, and the diameter over 2 is the radius capital R. So the radius capital R of the semicircle equals to 10 plus 2x over 2. 10 over 2 is 5, and 2x over 2 is x. So in total, actually found out that capital R, that is the radius of the big semicircle, equals to x plus 5 units in its length. Okay. So I write it down that capital R is the radius of the big semicircle according to our definition. And we just found out that the radius capital R of the big semicircle equals to x plus 5 units in its length. In the next step, we'll find out the length of the missing side, and we'll find out the length of the missing side. Here, this side is actually side edge M. We'll find out the length of this missing side, edge M. The missing side, edge M. The missing side, edge M, equals to AH, that is the radius of the big semicircle, minus AQ minus QM. Again, the missing side, edge M, equals to AH minus AQ minus QM. So I write it down. The missing side, edge M, equals to AQ, that is the radius of the big semicircle, minus AQ. AQ is 2, minus QM, that is x. So in total, the missing side, edge M, equals to AH. AH is the radius of the big semicircle. Is equals to capital R, and capital R equals to x plus 5. Minus AQ. AQ equals to 2, so we substitute AQ by 2, minus QM. QM equals to x. So in total, the missing side, edge M, equals to, here x minus x is 0, and 5 minus 2 is 3. So the missing side edge M equals to 3 units in its length. Actually, this is the missing side edge M. This equals to 3 units in its length. Here we have an internal notch between the big semicircle and this small circle. That is to say, the big semicircle touches this small circle at this point, internally at this point. They are touching each other internally at this point. Whenever you have an internal notch between two circles, you can implement rule 9. So I repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the drawing, we have two circles. They are touching each other. They touch each other, and at this point, point P, is their touching points. So they touch each other internally. It's point P. And according to this rule 9, the straight line that connects their centers together passes through their touching points. The center of the the center of this big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. This straight line OM passes through point P, that is the touching point. Again, the straight line OM passes through point P. Or ONP is one straight line. Again, OMP is one straight line. We can actually implement all 9 in our drawing. Why? Because in our drawing we have an internal notch between the big semicircle and this small circle. That is to say they are touching each other internally at this point. Therefore, we can implement all 9. The center of this big semicircle is here at point H. The center of this small circle is here at point K, and the straight line that connects the centers together is the straight line HK. So the straight line HK must pass through this touching point. They are touching points. So I'll join points H and K together by the straight line, and we know that the straight line HK must pass through this point that is their touching point. So you can see that the straight line HK passes through this point, that is their touching point. So we define the touching point of the small circle with the big semicircle. This point is point D. So you can see in the drawing that indeed the straight line HK that connects the centers together passes through point D. Or HKD is one straight line. Again, HKD is one straight line. If HKD is one straight line, it means that HD is a straight line. Again, HD is a straight line. But what is exactly the definition of the straight line HD? The straight line HD starts from point H, that is the center of the big semicircle, and then to point D, that is the point of the big semicircle itself. So this is exactly the definition of a radius. Therefore, HD is the radius of the big semicircle. This equals to capital R, and capital R equals to x plus 5. So HD equals to x plus 5 is the radius of the big semicircle. What is the definition of line segment KD? Actually, line segment KD starts from point K, that is the center of this small circle, and then at point D, that is a point on the small circle itself. So this is exactly the definition of a radius. Therefore, KD is the radius of this small circle. This is equal to x according to our definition. So in conclusion, we found out that HD is the radius of the big semicircle. This is equal to x plus 5, and KD is the radius of the small semicircle. HD is the radius of the big semicircle, that is equal to x plus 5, and KD is the radius of the small circle, that is equal to x. So what is the length of the missing side HK? The length of the missing side HK, from the drawing it is very easy to see that KH or HK, KH equals to DH minus DK. Again, DH minus DK equals to KH. So I write it down. So HK equals to DK, HK, KH equals to DH minus DK. Repeat again. The missing side HK equals to HD or DH minus DK. So the missing side HK equals to HD equals to x plus 5, this is the radius of the big semicircle, minus dk equals to x, it is the radius of the small circle. So in total we found out that the missing side HK equals to x plus 5 minus x. X minus x is 0, so we left only with 5. In conclusion, we found out that the missing side HK equals to 5 units in its length. This is the missing side KH, is equals to 5 units in its length, so I write it down. In the next step, I'll copy the right green triangle KMH in a new page, and we'll implement the Pythagoras theorem on this right green triangle KMH. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the equation for Pythagoras theorem. The hypotenuse KH equals to 5, side MH equals to 3 units, and KM equals to x, that is the radius of the small circle. So actually, this is the right green triangle KMH that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle KMH, KH square, this is the square of the hypotenuse, must be equal to KM square plus MH square. Again, KH square equals to KM square plus MH square. So I write it down. So KH squared, that is the square of the hypotenuse, equals to KM squared plus MH squared. The hypotenuse KH is 5, therefore KH squared is 5 squared, that is 25. and it is equal to km squared. Km is x, therefore km squared is x squared. Plus mh squared. Mh is 3, therefore mh squared is 3 squared, that is 9. So in conclusion, according to the Pythagoras theorem, we actually found out that 25 equals to x squared plus 9. Here we subtract 9 from this equation, and we get that x squared equals to 25 minus 9 is 16. So x squared equals to 16. We take out of this equation, and we get that x, that is the radius of the small circle, equals to the square root of 16, that is 4. So if we found out that the radius of this small circle, x, equals to 4 units in its length. Our mission is to find out the area of this small circle. We know that in general the area of any circle is equal to pi times the radius of the circle squared. This is the area of any circle, and therefore the area of this small circle must be equal to pi times the radius of this small circle squared. So the area of this small circle must be equal to pi times the radius of this small circle squared. The radius of this small circle is x, and the radius squared is x squared. So in total we actually found out that the area of this small circle equals to pi x squared. But we just right now found out that x squared equals to 16, so we can substitute x squared by 16. We do it now, we get that in total the area of the small circle equals to pi times 16, or 16 pi. So we found out that the area of this small circle equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. The area of the small circle equals either to 16 pi square units, or in terms of numbers, the area of this small circle equals to 50.265 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this small circle. So in the drawing, we have a big semicircle. We know that line segment AQ equals to 2 units in its length. This is line segment TB, that is equals to 8 units in its length. This is angle PQ8, that is a right angle. This is angle STB, it is also a right angle. Again, inside this big semicircle, we have this small circle, and our mission is to find out the area of this small circle. So, first of all, we define the relevant points to this question with letters. We defined the center of this big semicircle, this point is point L. We defined the center of this small semicircle, this point is point K. We defined the point of tendency of tangent PQ in this small circle, this point is point G. We define the point of tendency of tangent ST with this small circle, this point is point L. We define the point of tendency of tangent AB with this small circle, this point is point M. And finally, we define the point, the touching point of the big semicircle with this small circle, this point is point D. So here, we know that AB is the diameter of this big semicircle. So AB is the diameter, it is absolutely a straight line. AB is a straight line. Therefore, we can implement here rule 3. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have the upper side of AB at point Q? We have this angle, it is right angle, plus this missing angle. In total, it must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its sides. Likewise, we focus on the upper side of the straight line AB at point T. Here, the sum of the angles must be also equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points K and M together by a straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and ends at point M, that is the point on the small circle itself. So this is exactly the definition of radius. Therefore, Km is the radius of this small circle. We define the radius of this small circle as x, therefore Km equals to x. Here we can implement rule 1 because we have the radius Km is equal to x. The radius Km is drawn to point M, that is the point of tendency AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we join points K and G. We join points K and G together by a straight line. KG is the radius of this small circle, that is equal to x according to our definition. Again, the radius KG is drawn to point G, that is the point of tendency of tangent PQ with this small circle. Whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius QK. If PQ is perpendicular to tangent PQ, will be perpendicular to the radius GK. If PQ is perpendicular to GK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we created a quadrilateral GK MQ. Inside this small quadrilateral GK MQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral GK MQ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 angles must be its right angle if not a square. So we relate to this small quadrilateral GKMQ as a right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So an right angle GKMQ, side GK must be equal to the opposite side QM. But GK is x, therefore QM must be also equal to x. Likewise, according to the same rule, in the same right angle GKMQ, side KM must be equal to the opposite side GQ. But Km is x, therefore GQ must be also equal to x. So finally, actually, we found out that quadrilateral GKMQ is not a rectangle but a square, while because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. In the next step, we joined points K and L together by a straight line. KL is the radius of this small circle that is equal to x according to our definition. Again, the radius KL is equal to x. The radius KL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LK. If ST is perpendicular to LK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we created a quadrilateral, the small quadrilateral KLTM. Inside the small quadrilateral KLTM, we have 4 right angles. We have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral KLTM, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this right angle if not a square. So we relate to this small quadrilateral KLTM as a right angle because it has 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So an right angle KLTM, side KL must be equal to the opposite side TM. But KL is x, therefore TM must be also equal to x. Likewise, according to the same rule, in the same right angle KLTM, In rectangle KLTM, side KM must be equal to the opposite side TL. But KM is x, therefore TM must be also equal to x. Again, we actually found out that the small quadrilateral KLTM is not a rectangle but a square, why? Because of the fact that all of its sides are equal to each other. Each side equals to x. In the next step, focus on shape GLTQ. Shape GLTQ has 4 sides, 1, 2, 3, 4. Why? Because GL is the diameter of the small circle. Again, so I prove that GL is the diameter of this small circle. First of all, we note that angle GKL, this is again GKL, this is again GKL, that in total it is equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle JKL equals to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size must be a straight line. So GKL is a straight line. If GKL is a straight line, it means that GL is also a straight line. So GL is a straight line that touches the circle 2 points, G and L. Any straight line that touches the circle 2 points, it is defined as a chord. So GL is a chord, but GL is a chord that passes from point K, that is the center of this small circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, GL is the diameter of the small circle. So here, write it down, that GL is the diameter of the small circle. Again, GL is a diameter, it is absolutely a straight line. So, therefore, in the shape GLTQ, we have in total 1, 2, 3, 4 sides, and therefore, shape GLTQ is a quadrilateral because it has 4 sides. Okay? So, in quadrilateral GLTQ, we have 4 right angles, 1, 2, 3, 4. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we know this quadrilateral GLTQ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle GLTQ, side GL must be equal to the opposite side TQ. But GL equals to 2x. It is the diameter of the small circle. It is equals to 2x. So GL equals to 2x, therefore TQ must be also equal to 2x. So this line segment TQ equals to 2x. Now we can find out the radius of the big semicircle. We define the radius of this big semicircle as capital R, and capital R equals to the diameter AB over 2. So again, we define as capital R is the radius of the big semicircle, and capital R equals to the diameter AB over 2. What is the length of the diameter AB? The diameter AB of the big semicircle equals to in total to 2 plus 8, that is 10 plus 2x. Again, in total AB equals to 10 plus 2x. And again, the diameter AB in total equals to 10 plus 2x, and 10 plus 2x over 2 is the radius of the big semicircle, that is equals to capital R according to our definition. So capital R equals to 10 over 2 is 5, and 2x over 2 is x. So in total, capital R, that is the radius of this big semicircle, equals to x plus 5 units in its length. Okay, after I found out that the radius of this big semicircle equals to x plus 5, you can find out the length of the missing side edge M. What is the length of the missing side edge M? From the drawing it is very easy to see that edge M equals to edge A minus QM, edge A minus QA minus MQ equals to edge M. Again, edge M in total equals to edge A that is the radius of the big semicircle, minus QA, that is 2, minus MQ, that is X. So repeat again. The missing side edge M equals to edge A, that is the radius of the big semicircle, is equal to X plus 5, minus AQ, that is 2, minus QM, that is X. Again, edge M equals to A edge, that is the radius of the big semicircle, is equals to X plus 5, minus AQ. Again, AQ equals to 2, minus QM. QM equals to X. So in total, we found out that edge M equals to X plus 5 minus 2 minus X. X minus X is 0, and 5 minus 2 is 3. So in total, we found out that this missing side M edge equals to 3 units in its length. Now, we can implement rule 9 in our drawing. Why? Because in our drawing, we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at this point D. Whenever you have an internal notch between two circles, you can implement rule 9. Now repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching points. In the drawing, you have two circles. Those two circles touch each other internally at point P. This is point P. This is their touching point. So we have here an internal notch between those two circles. The center of the big circle is here at point O, the center of this small circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. So this straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. O and P is one straight line. Again, O and P is one straight line. So we can actually implement rule 9 in our drawing. Because in our drawing, we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at point D. Therefore, according to rule 9, the center of the big semicircle is here at point H. The center of this small circle is here at point K. And the straight line that connects the centers together is of course the straight line HK. And this straight line HK must pass through point D, that is their touching point. Or HKD is one straight line. Again, HKD is one straight line according to rule 9. If HKD is one straight line, it means that HD is also a straight line. So HD is a straight line according to rule 9. So what is exactly the definition of the straight line HD? The straight line HD starts from point H, that is the center of the big semicircle, and then at point D, that is the point of the big semicircle itself. Therefore, HD is the radius of the big semicircle, that equals to X plus 5. And again, we found out that HD is the radius of the big semicircle, that equals to X plus 5. What is the definition of line segment KD? Line segment KD starts from point K, that is the center of this small circle, and ends at point D, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, KD is the radius of this small circle, that is equal to X. And again, KD equals to X, it is the radius of the small circle. So what is the length of the missing side KH? The length of the missing side KH must be equal to DH minus DK. Again, DH minus DK equals to KH. DH minus DK equals to KH. KH equals to DH minus DK. So the missing side KH equals to DH, that is X plus 5. This the radius of the big semicircle is equal to X plus 5 minus KD. KD is the radius of the small circle, that's equal to X. So in total, the missing side HK equals to X plus 5 minus X. X plus 5 minus X is X minus X is 0, and we left only with 5. So actually found out that this missing side KH equals to 5 units in its length. In the next step, I copied this right green triangle in the new page and implemented the Pythagoras theorem in this green right triangle, triangle KHM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the spheres of the perpendiculars. This is the right green triangle, triangle KMH, that I copied from the original drawing. KM equals to X, it is the radius of the small circle. The hypotenuse KH equals to 5, and MH equals to 3 units in its length. So according to the Pythagoras theorem, in this triangle KMH, KH squared, that is the square of the hypotenuse, equals to KM squared plus MH squared. Again, KH squared equals to KM squared plus MH squared. KH is 5, therefore KH squared is 5 squared, that is 25, and it is equal to MH squared. MH is x, therefore MH squared is x squared. Again, Km is x, therefore Km squared is x squared plus MH squared. MH is 3, therefore MH squared is 3 squared, that is 9. So in total, according to the Pythagoras theorem, we actually found out that 25 equals to x squared plus 9. Here we subtracted 9 from this equation, and finally found out that x squared equals to 25 minus 9, that is 16. So x squared equals to 16. We took out of this equation and finally found out that x equals to the square root of 16, that is 4. That is to say, we found out that the radius x of this small circle equals to 4 units in its length. Our mission is to find out the area of this small circle. We know that in general the area of any circle equals to pi times the radius of the circle squared. Okay, therefore the area of this small circle must be equal to pi times the radius of this small circle squared. The radius of this small circle equals to x, therefore the radius squared is x squared. So in total, the area of this small circle must be equal to pi x squared. But we just right now found out that x squared equals to 16, so we can substitute x squared by 16. We did it and we found out actually that in total the area of this small circle equals to either 16 pi square units, or in terms of numbers, the area of this small circle equals to 50.265 square units. Okay, thank you very much.